We have begun. We've only just begun to talk. Another song. Moving on. So today, everybody, we are going to deal with. You nothing to be sorry. Why you no need to apologize to me?
Do you like Shakira?
What?
Do you like Shakira? Singer?
Yes.
Okay, that's what I was talking about.
Okay, cool.
Yeah.
The one who was married to the Spanish singer.
Well, they divorced.
Yeah, the divorce from. Yeah. Oh, yeah. Oh,
All of that.
she's about 5 to 10 years older than he. Interestingly enough, great soccer player. Now, that's talk about a celebrity, and you're a star for Barcelona in Spain. You're playing the Palace.
Yeah.
No question. All right, moving on, everybody. Sliding filament model of contraction. She did rather her halftime show with J Lo was pretty.
It was good.
Yeah, I thought it was great. I told Dr. Hillwig, and she looked at me and goes, "My boys were entirely too interested."
Yeah, what she expects.
Hey, that's okay. What are you going to say? All right, moving on. So, ladies and gentlemen, sliding filament model of contraction. It's not just one thing. It's a series of things. What they will show you initially is the sliding filament model, which you probably have seen. But we're really going to go into detail about this because we have to. And then we're going to look at the events. There's 3 series of events. The new events at the neuromuscular junction, something called excitation, contraction, coupling. That's the transition from electrical energy to mechanical energy, transduction. And then finally, the cross-bridge cycle. I'm not sure we're going to get to everything today because there's a lot of steps. Maybe we'll talk about it and summarize. The activation of cross bridges to generate force. That's what contraction is, the sliding of the filaments over one another. So, and basically, when do we get motion? I mean, it's more physics that I'm not. When energy is sufficient to overcome whatever the object is. I mean, you can push on a bridge, and we'll talk about isometrics versus isotonics. So we look at the relaxed state of an individual, because you just look at a sarcomere and just mentally think of the millions and millions of them in sequence. Thin and thick filaments overlap only slightly at the edges of the A band. Okay, and that defines the A band as the overlap because it obscures light to some extent. So during contraction, ladies, it's like high school, I have to separate
I'm very
you.
excited about contraction. We're very passionate.
I'm going to send you to the principal's office. And I wouldn't be your first trip, I suspect.
I could. But we can get off topic yet. Dr. Stein, whenever you want to get off topic, let me know.
I'll make a note of it. So, that familiarity is just too much. Thin filaments slide past thick filaments, causing actin and myosin to overlap, and you're going to see an enhancement, or rather more of a continuous nature of the dark or the A band. There's no length change, no folding or bending. This is just sliding, and we're seeing it visibly. So, and effectively what's happening, what causes this, we've talked about a little, and we'll get into in detail, is the formation of those cross bridges. So, and again, this is the part I pointed out with the offset nature of the myosin heads, that they form and break. The more you're using the muscle, the more you're trying to contract it, the more they break and reform, but not all at the same time. It's very much offsets that are there, pulling it all toward the midline. So you're going to see an apparent, it's visual, it's an optical illusion. The eye bands, it's really not an illusion so much. The eye bands themselves appear shorter because the A band basically appears more distinctively that are there, and you're shortening from a lengthwise perspective the sarcomere. So since the actin filaments are attached to the Z discs, they're pulling them closer together. So here we are, and we'll go flip-flop between these two. So this is relaxed. You can see that mid zone or the H zone, reminiscent of the letter H. You can see it's dark. Look at the size of the individual light band or eye band areas on either side. Okay, and so this is what it looks like. There's a sufficient amount of overlap to permit motion, but there's still plenty of room for these fibers to continue, these filaments rather, and I do that all the time, to continue to overlap. So when we move it, now notice the A bands is really the same length, but it's continuous. You don't see that H zone in the middle, and the I bands have shortened. And look here, if I put my cursor over where the Z disc is, now look, so it'll change from here it is forward, here it is backward. That's the amount of contraction. The movement of that Z disc from where it is here to now where it was originally. And so even though it's not a dramatic apparent change other than this portion disappearing and these moving closer together, if you magnify that by thousands of individual units or more, then you see a real distinct change. So that's really a telling image about, and we can obviously tell microscopically whether we're looking at something contracted or, because something might be in a permanent spasm, you can see that. There might be of some forensic value if you're looking for a toxin, things like that. But without going crazy over that, background and overview. It's voluntary. You're moving the muscle. For the most part, we do, for distinct, not for things that we sort of do subconsciously, walking, coming in. It's not like we're saying, oh, grab this, grab that. So it activates from our brain, sending the signal down the motor nerves. We did the anatomy of the brain. We looked a little bit at the tracks. It's called, basically it's called the corticospinal tracks that are going from the cerebral cortex down the spinal cord, and from the spinal cord out to the muscle. It's a 2-nerve unit. Our focus for now is going to be on the nerve going into the muscle, and therefore the neuromuscular junction. Effectively, it's a synapse, or if you want to say synapse, it's fine with me. It's a synaptic junction. Those are junctions between nerves and nerves, or nerves and muscles. That's it. All it is. So the excitable nature of nerves and muscles plays a pivotal role in it. They're capable of changing the resting membrane potential voltages. And when an action potential is generated, when you say move this, okay, that eventual destination of what you're moving is going to be a muscle from your spinal cord, or perhaps your brain, if it's a cranial nerve, going to the muscle and releasing a neurotransmitter, a granule, a liquid, a substance, better way to express it, called acetylcholine or acetylcholine. It doesn't matter how you pronounce it. It's a junction of a very common product we have everywhere, acetic acid, which we use in multiple things, and an interesting substance, a nitrogenated organic substance called choline. Okay. And you're going to see as we move on, we do a pretty good job of conservation. We recycle a lot. The choline effectively is all recycled. You'll see what goes on. So, but that's the first of the big neurotransmitters, and fortunately, because it's the one we have the most of, we use the most of. It's part of our. It's really the pivotal substance at the neuromuscular junctions. The only thing that really is used is acetylcholine, certainly for skeletal muscles, number one. Certainly plays a role in cardiac muscles, perhaps a little bit of a role in smooth muscle that is there. It is abundant in our brain. It is 3 of the 4 juncture points in the sympathetic and parasympathetic systems, both in the parasympathetic, one in the sympathetic, utilize acetylcholine as a neurotransmitter. What's a neurotransmitter? Something that spits out at the end of the nerve, where it's exocytosed. When I started to teach, when you went to get a job at a college to teach, you usually had to do a teaching demo. So you get in front of you maybe have done this. Hey, we're going to look at some new faculty members. We've done this here. We were going to add another A&P person, but they ran out of money. So like Dr. Hillig, when she came here, which was a year after I came on board full-time, Dr. Hanner and I did, you do a teaching demo. And so I always did neurotransmitters. And because my daughter suggested, I said, what could I use to represent things spitting out of a nerve? And she said, pixie sticks. Works for me. And so and they come in 5 different colors, and they're 5 major neurotransmitters. How you like that? Sounds good. And of course, there was never any left over. Moving on. So we have different kinds of channels that some of which, and the ones we're going to talk about mostly here have to do with the movement of charged particles. So we call them ion channels. And we're going to explore two varieties, voltage gated ones that rely on an action potential passing next to them and quickly changing the polarity of the surrounding membrane, and ligand gated channels where chemical bonds to open the passageway for the ions. Acetylcholine is a chemical. So first, when we look at so far is a ligand gated channel. You're going to see it's not the first one in initiating your muscles to move. Actually, it's a voltage gated channel. More on that later. So chemically gated or ligand gated ion channels, neurotransmitters, acetylcholine, great example. Voltage gated ion channels, when you tell that nerve to move something, that action potential is going from, let's say, your spinal cord down to a nerve going to your leg or to your arm. And when it gets to the terminus of the nerve, the bulb or the axonal bulb, where the synaptic vesicles are located, it doesn't trigger them directly, but indirectly, because at the terminus of that nerve is a voltage-gated calcium channel. Calcium plays a big role in the neuromuscular system and in nerve physiology because it starts with calcium and to some extent it ends with calcium. It's all about, so now you start to see one of the sort of the together points of art, and I touched on it a little bit last time. Those positively charged particles, sodium and potassium, setting up resting membrane potential, and calcium everywhere. Blood clotting, respiratory, any physiological system. We are replete with calcium. So calcium levels are big time players. Those positively charged particles play a big role. So here we are. Here's the ligand binding versus a voltage channel where it has nothing to do with the chemical. It's just a flip-flopping, the rapid change of polarity. And you'll note down the road, we're going to look at that guy over there. That little guy there plays a role. It's called an inactivation gate. And what it does, it's one thing to, if you want to think of those channels as doorways, a door can be open or closed. Here it's open, here it's open. But when we close the door, it's relatively easy to open, like that door. Okay? Think of this as a lock. Inactivate, and it plays a role in a very important process when we get to cardiac, okay, which is called the absolute refractory period. Skeletal muscles, we can use them until they fatigue very, very rapidly. Okay. Cardiac muscles have a great contract with the body. It takes about a quarter of a second for them to contract, then they get to rest for a quarter of a second. I love that. That's like me at home. I walk the dog. I don't have to do anything for the next hour. Doesn't work that way. Not on an effing day. Did you take out the garbage? No, but I will right now. It's all coming. My dad's sage advice that I didn't, it's only two things I didn't listen to my dad. One with my first wife, he goes, I know you're getting married, but I wouldn't marry her. And the other one, stay single like your old man. So, didn't follow either one of those. Sid, I should have listened. Okay, anatomy of motor neurons and the neuromuscular junction. So these by definition are somatic motor neurons, meaning they're going to body structures, particularly muscles, joints, things like that. We'll get more in detail into my version of neuroanatomy when we start looking specifically at the nerves themselves. That's the next chapter. But the long transmitting or message carrying tail is called an axon. Very much, a thread is a very good description. They can be a meter long. I mean, it's a two nerve circuit. If you have somebody who's 6'5", basketball player like that, from their brain to the lobe, to the lumbar area, lumbosacral area, about a meter. Same distance going to their toes. So it's a 2 nerve circuits, but they're infinitely, extraordinarily skinny, invisible. It branches as it enters the muscles and forms a multiple area of neuromuscular junctions. So you're going to begin to see that. And where this occurs is a unique protein structure called the motor end plate. And the way that they depict it here is pretty good for motor end plates. It's a modified protein receptor area that, again, it's designed to create an ample amount of surface area. And that surface area creates a lot of potential ligand triggered passageways. And depending on how many of those are triggered, based on how much neurotransmitter and how many groups are activated, may or may not generate an action potential. So nerves are constantly doing little bits of firing. We don't always sense it or see movement. They're developing what we call end plate potentials. A little bit of neurotransmitter coming out, if it doesn't reach threshold, it's not going to produce any action. And you do this, and not this Monday, but the following Monday, we'll do the technology lab with electromyographic aspects. In other words, we're going to see about electricity when you use muscle, how it fatigues. So here's what it looks like. So here's a motor neuron. And notice the first thing, they don't all go to the same fibril. They don't go to the same location. And this is by design. Well done up there. Keep up the good work. Okay. Hey, remember, if I have a bet on the Super Bowl, I'm in a Super Bowl pool. We like you buy squares. It's like 10 by 10, so it's 100 squares. And you buy them for, let's say, $1. And, if you're in, they draw numbers, and like the final score is 21-17, and you have a 1 and a 7, you'd win a substantial amount of money. This one's a little different, but same idea. More than $1, however. It's my son's fault. It's one of his buddies from the Navy who got out, and he's a high school principal. He runs these pools. Sir.
Does every fiber have to have axon terminal?
Yeah. Effectively, they're all potentially triggerable. I mean, some of them are used only rarely, okay, but they all are triggerable. So by the design is here is to prevent fatigue. So it's like if you're lifting something, it'll be several areas, not all on the same strand. So it doesn't overdo one particular fibril. It allows it, and then as you engage more, it engages more and more areas, some in the same location, some in different. So effectively, it's trying to limit fatigue. You're doing it. And depending on the composition of the muscle, as we'll see, which is somewhat hereditarily based, there are certain ones that do certain things better than others. Like certain folks who are, why can't we all be an Olympic sprinter? Well, not just from training and dedication, but there's a certain amount of muscle. Like I said it today, I have a vertical leap of about a half an inch. I'm not going to be Michael Jordan. Okay. The reason Michael Jordan is at least partially genetically. Depends on we'll talk about different fibers. So at the end of the axon, we call it the synapse or synaptic cleft. They both apply. It's a molecular space, but it's a space. The ends don't touch. They are as close to each other as you could possibly imagine. So only molecular. So when we exocytose the neurotransmitter in whatever form it is, granular, liquid, solid, semi-solid, and it doesn't really matter. It's because most of it's dissolved. It has a very short journey. If it once it gets exocytosed and spits out, it's going to contact the receptors. It's as close as you could imagine microscopically without touching. Okay? So they contain the acetylcholine. The sarcolemma has these infolds they call junctional folds and then they're embedded with the protein ligand-based receptors. So the junction has the terminus of the axon, or bulb, if you want to call it that, the cleft, and the folds. And here it is depicted. So what do we see? We see an abundance of synaptic vesicles filled with acetylcholine. We see an abundance, and even though you don't see it here, of mitochondria. It's very energetic dependent. What is this over here? Those are the areas of voltage-gated calcium channels. And this is calcium from outside the nerve in the extracellular fluid coming in. And there's a big distinction when we talk about calcium with troponin and tropomyosin. That's intracellular calcium. It gets spit into the cytoplasm, or the sarcoplasm, as you would call it, and then gets pulled back into those wells to store. Very little reliance on extracellular calcium. So calcium, again, is very, very specific. This is, it basically opens the doorway or pathway as the action potential comes down for the calcium to enter. What does the calcium do? You should already know that from cell and molecular. Okay? Calcium basically initiates that bonding of the synaptic vesicles together, basically that latching together that we see associated with the vesicles. So moving on. So the big picture. We're going to look now, and what we're looking at is neuromuscular junction. We're going to look at the excitation that occurs as an action potential is developed. We're going to see how it leads to excitation, contraction, coupling, translation from electrical to mechanical, and then finally, actually how the sliding occurs. So it's, again, that's one of the things these books don't do well, is these illustrations are too hard. So basically, the nerve fires in action. It goes down and it induces the release of acetylcholine. It didn't even talk about those voltage-gated calcium channels. Yeah. Acetylcholine binds to the folds of the receptors. You can see it floods this area with all the surface area and all the receptors. Effectively, every one of those opens, you get that 3-to-2 relationship. Sodium going in, potassium going out. What's the net of 3 positive charges going in and 2 positive charges leaving? An increase of the resting membrane potential, which is roughly minus 70, for argument's sake, negative, moving its way up. So those are end plate potentials, EPPs, and if they reach threshold, we trigger an action potential. The action potential, by definition, local potentials get to like here. And again, we sum up all the events. When it generates a number of local potential to go, say, to here, then it's going to trigger voltage-gated sodium and then potassium channels. So we start voltage-gated calcium, then that triggers ligand-gated acetylcholine channels, then those channels are sodium and potassium, and finally, if we reach threshold in an action potential, then we're going to generate enough of a change to reach and start a chain reaction of voltage-gated sodium and potassium channels. So that's a fascinating construct. That action potential then travels along the sarcolemma, down the T-tubules, triggering yet again voltage-gated calcium channels, releasing intracellular calcium at the triads, at the terminals of sterni. Calcium then binds to troponin, moves it out of position, allows tropomyosin to move out of position, and voila, now it exposes those active sites on respectively the actin and myosin, and we get contraction, ratchet, whatever you want to call it.
Okay,
That took some time.
it was good.
So these, I hate to say it, you need to memorize these steps. Yeah,
Like they're gonna be on.
yeah. I like mostly in the form of a sequence question. You know,
Which
which
you
is,
put a number next to it?
I probably, you can do whatever you want.
Okay.
As long as you remember it. I don't care. You're smart.
Whoa. The slander today from the wreck. Why? Getting bullied today, Dr. Stein. You're helping.
It's all because there was no internet this morning and we were all flipping
Oh, that's why? That's why we're bullying me?
out.
Great.
When I came in and turned on my computer, it goes, your Wi-Fi's off. No, it's not. I left it on. And I couldn't turn it back on. It was very embarrassing. Well, okay, so action potential. You made that. Voltage-gated calcium channels. Calcium enters. Calcium basically induces the eventual relief of the synaptic vesicles. They diffuse across. Sodium, actually, they're sodium-potassium gates. Binding allows sodium to enter. And then we'll talk a little bit about how we get it all out of there, because it recycles very quickly. And that has to do, there are 3 ways that we remove the acetylcholine from that relatively small area of synapse, as you will see. And it's interesting because when we talk about generically about neurotransmitters, there's 3 ways that they are removed. Acetylcholine, to some extent, at the neuromuscular junction, demonstrates all 3. Some of it just diffuses away because you release a lot and it diffuses away from the region. Fine. Easy to understand. Not the biggest component. Some are metabolized or broken down into acetic acid and choline. Okay. When they are not, if it's not acetylcholine, it's no longer going to have an impact. That's facilitated by this enzyme, the name's easy to remember, acetylcholine esterase. Because it's effectively, what's an ester? Organic chemistry, how do you make an ester? How do you esterify something? Well, you MCAT people, that would be something I would know, like what's an amide, what's an ester. When you mix an alcohol and an acid, you get an ester. When you mix an you get an amide when you have, it's like a peptide bond. So you have like an NH group with a COOH group. See, those are the kinds of things for you MCAT folks and standardized test folks that you should file in your memory bank. So acetylcholine esterase, that enzyme degrades, breaks down, metabolizes it. Acetic acid is able to move away. We use it a lot of places biologically. The choline undergoes, and this is the third of the processes, diffusion, metabolism or breakdown. The third process, reuptake. It pulls the choline back in. It travels up by those neurofibrils back toward the cell body, quote unquote, nucleus of the nerve cell to reform more acetylcholine. Happy dance. Acetylcholine was the first of the neurotransmitters because they isolated it from the vagus nerve and saw what it did to the heart, how it slowed down the heart rate. Okay, that's how the vagus nerve got named. And it was vagus stuff that came out of the vagus nerve, and later we named it acetylcholine. So here we are, action potential arriving, coming down there. And so this is depicting myelinated versus non-myelinated. You can see the typical fibril or cell, rather the typical cell, and eventually getting down to the fibril level. We saw that before. So you can't really see it, but this is the voltage-gated calcium channels. Calcium from outside of the nerve cell and outside of the junction flowing in. Okay, calcium entry, effectively what it does is it facilitates those V snares and T snares that latch on and create the exocytosis. That action that's blocked by Botox, that blocks that from occurring, and that's why it's a paralytic agent. Okay, Botox by definition is not spastic paralysis. Botox by definition is flaccid paralysis. So what happens is the nerve can't fire and it relaxes. That's why originally it was being used for wrinkles and things like that. We use it for a lot of stuff. Unless you're about 6 months duration in the body. So acetylcholine diffuses across the synaptic cleft, binds the receptors, and then we have that, and you can barely read it. Sodium going in, potassium out, the consistency of that 3-to-2 relationship. 3 sodiums in, 2 potassiums out. And then they're talking lastly here in these relatively poor slides about terminated by the breakdown metabolism of at the synaptic cleft by acetylcholinesterase, by diffusion. And what they don't comment on here but should is the fact that the choline is reutilized or reuptaken. Which brings us to our first. I do not know how the sound will play, but if I have to adjust it, I shall.
Nerve impulses, also known as action potentials, travel from the brain or spinal cord to trigger the contraction of skeletal muscles. An action potential propagates down a motor neuron to a skeletal muscle fiber. The site where a motor neuron excites a skeletal muscle fiber is called the neuromuscular junction. This junction is a chemical synapse consisting of the points of contact between the axon terminals of a motor neuron and the motor end plate of a skeletal muscle fiber. The events at the neuromuscular junction occur in 7 coordinated steps. Step 1. An action potential travels the length of the axon of a motor neuron to an axon terminal. Step 2. Voltage-gated calcium channels open and calcium ions diffuse into the terminal. Step 3. Calcium entry causes synaptic vesicles to release acetylcholine via exocytosis. Step 4. Acetylcholine diffuses across the synaptic cleft and binds to acetylcholine receptors, which contain ligand-gated cation channels. Step 5. These ligand-gated cation channels open. Step 6. Sodium ions, shown here in red, enter the muscle fiber, and potassium ions, shown here in blue, exit the muscle fiber. The greater inward flux of sodium ions relative to the outward flux of potassium ions causes the membrane potential to become less negative. Step 7. Once the membrane potential reaches a threshold value, an action potential propagates along the sarcolemma. Neural transmission to a muscle fiber ceases when acetylcholine is removed from the synaptic cleft. This removal occurs in 2 ways. 1. Acetylcholine diffuses away from the synapse. 2. Acetylcholine is broken down by the enzyme acetylcholinesterase to acetic acid and choline. Choline is then transported into the axon terminal for the resynthesis of acetylcholine.
That's the reuptake. Are we done? Sounds like we're done. Those are good. And there's 2 more like that that are all very, very good. So this is just some of the events that occur. And those of you going into medical fields, you see those things. If I saw them, you see them. You know, they aren't extraordinarily common, but myasthenia gravis. And remember, muscles that we use the most fatigue the fastest. So it typically presents itself with drooping eyelids, because the first thing somebody, with bells and whistles go off in a clinician, I'm having trouble keeping my eyes open. I get sleep, and all of a sudden I just can't see that. Ding, 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 ding. We swallow a lot, we talk, and then generalize. So you look at the progression. Diagnostics are so much fun to do that stuff. I love that. That was the greatest thrill I had, to make a diagnosis, particularly if someone else didn't. That's what I miss. It's sort of like the whodunit value. Okay. Shortage of acetylcholine receptors. This is the autoimmune disease, and we think that's probably more in line with myasthenia gravis. And there's a lot of medications that are, quote, acetylcholinesterase inhibitors that can be used at the neuromuscular junction. They also have they have other negative usages as well, which we will get to. So we know it's polarized. We talked about resting membrane potential with the cell. It's just not a whole lot different. The difference is this one can actually change rapidly. And so, well, how are we able to generate the action potential? We start with an end plate potential. The fact that some of the ligand is causing a subtle change. If that change reaches, okay, threshold, we will have depolarization, a rapid shift brought about by sodium flooding in, and then reversed or repolarized, reset, whatever makes sense to you, of potassium going out. In the meantime, now we got a whole bunch of extra sodium in and a whole bunch of extra potassium out. That's not the resting conditions, and that means anytime we do something in a nerve or a muscle, now those wonderful sodium potassium pumps, active transport, have to reset this. So they're working constantly to reset the cell. So acetylcholine is released, binds chemical gated ion channels. We did that. Sodium in, potassium out, not much. Sodium diffuses in, less positive. I like that. It's like glass half full, glass half empty. Less negative or more positive. I'm a more positive. I saw my doctor yesterday morning, and the intake nurse goes, "Are you suffering from depression?" I said, "Just the opposite. My wife tells me I'm always in a good mood."
That's good.
I'm not moody at all. You know, the Steelers lose, I'm moody. Manchester United loses, I'm moody. So they call those end plate potentials at EPP. So what happens if the end plate potential reaches threshold? And threshold is, let's say, typically something along the lines of, if we're minus 70 is the average, maybe minus 55. So moving up in millivolts up to that area, sodium channels in the membrane will open. These are voltage gated channels. So once we flip that membrane to reach those, watch out, because that sets up the chain reaction. Sodium ones open the potassium ones next to them. The potassium ones open, they open the sodium ones next to them, and so on. It's that rapid flip-flopping from positive outside to negative inside, immediately across the membrane, back and forth, back and forth. And it's multi-directional. So if you stimulate that muscle fiber here, it's going that way, this way. It's not directional. When we get to nerves, directional. And that's what's going to bring into play those inactivation gates a little bit more. That's a subtle difference that you're going to see. They play much less of a role here. So it spreads from one voltage gated channel to the next, until depolarization is complete. So here it goes. Boom. The end plate potential starts here, depolarization, sodium channels, electrical chemical gradient, generated, etc. Then it's better to see the animation than the blabbing. We restore it again. Sodium voltage gated channels close, voltage gated potassium channels open. There is a brief refraction. We're gonna as we go on, looking at nerve, muscle, cardiac, we're going to talk about absolute and relative refractory periods. What I talked about with the heart is an absolute refractory period. It will not undergo another action potential. A relative refractory period with enough of an oomph, it'll re-go. And we can induce that, and do induce that by choice in physical therapy modalities, which I have a certain degree of familiarity. Okay? So understand that's, again, this has to do a little bit with the inactivation gates. They are much less of a factor in the skeletal system than some other systems. So ionic conditions are restored by the sodium potassium pumps. Voila, they're going to show you this stuff again. This is the idea. It's a sharp spike. When we get to heart, you're going to see it. The spike doesn't look the same. There's more of a plateau created. That's because the heart, it has to do with maintaining the contraction of the heart for a certain amount of time to facilitate the blood being pushed out of the ventricles in its entirety, let's say. So it's like this. Okay, and you notice the time factor. We're talking about what? Less than 10 milliseconds? That's where the origination of the term PDQ. Pretty darn quick. Do you know that?
I like that.
It's not, I didn't invent it.
No, but you just tell people you did.
I can't even tell. It's like, you know what a snafu is? Situation, normal, all FU'd. And then there's tarfu, things are really FU'd. And FUBAR, FU'd beyond all recognition. Those are military terms. They use a lot of salty language in the military. I have a son, and they drink a lot of beer.
Good for them.
Oh, I have never seen a refrigerator with more beer, or a cabinet, fairly generous size cabinet filled with more bourbon. What are you smiling about?
I'm smiling. I've never drank beer when it's not
Just a bourbon girl.
Yeah, actually. Yeah.
I never appealed to me. No.
Are you a wine guy?
No. I'll have a beer every now.
Tequila?
No. I'll have a beer. I think I'm having dinner with my wife, and I'm having dinner with my daughter and her fiance. I'm sure there'll be some alcohol.
Yeah, maybe.
Excitation, contraction, coupling. Okay. This is when we bring them together. So you'll see the video and we'll go. It's propagated along the sarcolemma, down the T tubules, at those voltage gated or voltage sensitive proteins in the tubules that sort of adjacent to or incorporated with the ones in the terminal cisternae. Intracellular calcium stored there is released, and boom, there we go. So you'll take a look at the sequence of events. This is the here's the action potential going in and around the individual fibrils facilitated by the construction of sarcoplasmic, the T-tube is part of the sarcolemma. Here are those juncture points between the cisternae where the voltage sensitive things are there. The calcium then enters, floods the interior of the fibril and around the filaments, attaches to the troponin, the tropomyosin. Once it alters the shape of the troponin plugs, the tropomyosin shifts, and voila, we have contraction. And that's what they're showing you. So take a look at this. It's probably what we'll all have time for.
Typically, a single motor neuron arising in the brain or spinal
Very good
cord
illustration
conducts action
of the
potentials that travel
T
to hundreds of skeletal muscle fibers within a muscle. The sequence of events that converts action potentials in a muscle fiber to a contraction is known as excitation-contraction coupling. If we look at a single muscle fiber, we see that an action potential travels across the entire
those are the
sarcolemma
T-tubules.
and is rapidly conducted into the interior of the muscle fiber by structures called transverse tubules. Transverse, or T-tubules, are regularly spaced enfoldings of the sarcolemma that branch extensively throughout the muscle fiber. At numerous junctions, the T-tubules make contact with the calcium-storing membranous network known as a sarcoplasmic reticulum, or SR. Where it abuts the T-tubule, the SR forms sac-like bulges called terminal cisternae. One portion of a T-tubule plus two adjacent terminal cisternae is known as a triad. The membranes of the T-tubule and terminal cisternae are linked by a series of proteins that control calcium release. As an action potential travels down the T-tubule, it causes a voltage-sensitive protein to change shape. This shape change opens a calcium release channel in the SR, allowing calcium ions to flood the sarcoplasm. This rapid influx of calcium triggers a contraction of the skeletal muscle fiber. Thus, Calcium ions are responsible for the coupling of excitation to the contraction of skeletal muscle fibers.
And so that's really that energy transduction, which we see in so many different areas, anatomically and physiologically. So when we don't have calcium in there, the tropomyosin threads are in position. They block those active sites on the actin so they can't jump or join the sites on the myosin heads. It's relaxed. When the calcium is released and creates high intracellular levels, it binds to troponin. It changes its shape like a little plug. It allows the tropomyosin to quote unquote slip out of position. The cross bridge, because the heads are exposed on the active sites, they cross bridge. And as long as it's the calcium is there, it will continue to cycle. What keeps the calcium there, a greater amount of neurotransmitter prolonging the initiating events when you have to lift something heavier than you thought. Or, when you start, and then you determine how much more oomph you have to put in it, so to speak. So we'll stop it there. Is there something you wanted to do now that we're on non-fun?
Yeah, if you were a dinosaur, what dinosaur would you be?
Oh,
That's good waiting.
oh,
Do it.
oh, I gotta think. My initial thing was a stegosaurus.
Okay, oh, I can see you as a stegosaurus.
I like that.